So let's talk about chemical equilibrium today. So when we are talking about chemical equilibrium, imagine you are filling a bucket with water. At the same time, water is leaking out at the bottom. Now water going in is equal to water coming out. The water level stays the same. The situation is what we call equilibrium. Now in chemistry, chemical equilibrium happens when the rate of the forward reaction equals the rate of the backward reaction. So the reactants and products are still changing, but their concentration remain constant. So that's chemical equilibrium. Now, many students usually confuse what we call dynamic equilibrium and chemical equilibrium. So when we are talking about chemical equilibrium applies to chemical reactions, but dynamic equilibrium describes how equilibrium happens. So dynamic equilibrium describe how equilibrium happens. Dynamic means forward reaction is happening, backward reaction is happening also, both happen at the same time and the same rate. So equilibrium is dynamic in nature. So here is the example. For example, we have so here is the example. For example, we have For example, we have N2, which is a gas, plus 3H2. So for example, we have that reaction, nitrogen plus hydrogen, which is giving us what? Which is forming ammonia. So at the same time, ammonia is breaking back into nitrogen and hydrogen. So nitrogen and hydrogen are forming ammonia. At the same time, ammonia is breaking back into nitrogen and hydrogen. So this reaction is what we call chemical equilibrium. Now let's look at something that we call equilibrium constant. So at equilibrium, we can describe the reaction using a number called the equilibrium constant. And this equilibrium constant tells us how much product and reactant exist at equilibrium. It helps us to answer, are there more products or are there more reactants? So let's start with KC. Let's start with KC, which is equilibrium constant in terms of what? In terms of concentration. So you'll be seeing this one, which is KC. Now here is the general rule. When you are given a reaction like this one, which is AA plus BB, so these small letters just represent the coefficients. Now when you are given this, the equilibrium expression is written like this. Kc, which is the equilibrium constant, is equal to, so the capital letters, we put them like this. Then so we start with the products over the reactants. Now after putting the capital letter, the small letter goes on top. So this is how we write the equilibrium expression. So it's product over the what? The reactants. Now square brackets, these square brackets, they mean concentration in mole per cubic decimeter. Now just as I said, so the game here is the products over the reactants, but these products, after putting them in the brackets, which is meaning concentration, you raise them to their what? To their to their coefficients. For example, C here has a coefficient of C. That's why we have raised it to the power C. Even D has the coefficient of small letter d. We have raised it to power small letter d. Same applies to the what? To the reactants down there. Now, given this example, we have hydrogen plus I2, which is equal to 2Hi. Now, can you write the equilibrium expression? So, just as I said, we say Kc is equal to the products. So, the products, it's Hi. Now, what's the coefficient of the products? The coefficient of the products is 2. So, we raise to the power 2 over what are the reactants. So, we start with H2, which has no coefficient. So, we put H2 power 1 times I2, which is also power 1. So, this is the equilibrium expression. So, products on the top, reactants at the bottom, powers come from coefficients. Now, if you had the concentration of Hi, the concentration of H2, the concentration of I2, you would find the numerical value for what? For the equilibrium constant. Let's try again and do an example with the values. Now, for this one, we have 2SO2 plus O2 gas is equal to 2SO3. Now, for this one also I won't give the concentrations, so that we are just fluent with how to write the equilibrium expression. So our Kc will be equal to, so it will be equal to SO3 power 2. As we can see, the products have the coefficient of 2, so we have raised to power 2. Also, the reactants, we start with SO2, which has the coefficient of 2, so we have raised it to power 2, and O2 has the coefficient of 1, so we just raise it to power 1. So at the end, this will be our equilibrium expression. Now, let's look at an example where we have the values for concentration. Now, given the concentrations of H2 and I2 to be 0.2 and the concentration of Hi to be 0.8. Now, how do we find the Kc? Kc, we just say products over reactants. What are the products? It's 0.8 only. So we say 0.8 power 2 over, what about the products, the reactants? So the reactants, we have 0.2 times 0.2 because they all have coefficients of 1. At the end, the answer we are going to find is what? Is 16. So this 16 is what we call our equilibrium constant. So this is just how we calculate. So maybe you are wondering how I was putting this 0.8. So here where there is 0.8, at first there is supposed to be Hi power 2. Now, as I said, the brackets mean concentration. So what's the concentration? The concentration is what? Is 0.8. Now, what does the value of Kc tells us? And this is very important for exams. So the value of Kc, for example, if Kc is greater than 1, then that means products are much more than reactants. So reaction goes almost to completion. For example, the equilibrium constant is 100, or the same 16 we have found. It means there are more products. So that's what the equilibrium constant tells us. So small Kc means reactants are much more than products. And for this one, reaction hardly proceeds. Now let's look at equilibrium constant in terms of pressure. As I said earlier, that was equilibrium constant in terms of concentrations, and we represent it by Kc. Now, what about pressure? Equilibrium constant in terms of pressure, we represent it by Kp. So Kp is the equilibrium constant written using partial pressures instead of what? Of concentrations. So for example, N2, which is gas, plus hydrogen, which is gas, which is equal to 2NH3, which is ammonia, which is also gas. Now our Kp will be PNH3 squared, because the ammonia there has the coefficient of 2, so we have raised it to power 2, over the reactant, which is PN2 times H2 power 3, because hydrogen has the coefficient of 3. Now, what you can notice here, the difference between Kc and Kp, instead of putting the brackets, where those square brackets, we are just using the normal brackets, and we are introducing the P. P meaning the partial pressures. So this is how we represent the what? The Kp. So we use pressure instead of concentration, and also concentration still become what? Powers. Let's try to do an example. Given the 2NO2 gas, which is equal to N2O4 gas, how can we write the equilibrium expression now in terms of Kp? So this is going to be Kp is equal to NO2 squared. This is a squared. Yeah, that's our Kp. Let's look at problem 2. Now this one is just to cement on what we have talked about. So this one is if Kc for a reaction is very large, what does it mean? So when Kc is large for a reaction, it means there is large amounts of products, and the reactant strongly favors what? Reaction strongly favors products. So that's what we talked about. So this is all about chemical equilibrium. Now the important notes that we should know is only include gases and aqueous substances in Kc and Kp, and solids and pure liquids are not included. Coefficients become powers. Products only go on what? On top. So in this video we have understood chemical equilibrium, seen why it's dynamic, learned equilibrium constants, written Kc and Kp expressions. We have also interpreted large and small Kc values. So the topic continues in the next video, where we will look at the main thing that we are going to look at also, chemical equilibrium. So don't forget to watch the next video also, and also don't forget to like and subscribe for